Welcome to BD Deep Dive, where ideas go deeper. Today's story is a war story, but instead of tanks, it's cables, switches, and tiny packets of gradients fighting for their lives. The battle: who controls the connections between GPUs? Because that's increasingly where AI performance lives or dies.
I love that the most expensive computers on Earth are now limited by, basically, group chat speed. So when we say connectivity war, are we talking inside a server, across a rack, or like the whole internet got drafted?
Exactly the right question, because the core claim here is model size exploded and the bottleneck shifted from compute to communication. Training isn't just do math faster, it's synchronize faster, moving gradients, weights, activations, so the GPUs agree on reality often enough to learn.
So the GPUs are like a team of chefs. Each one cooks a dish, but then they keep running back to compare notes after every chop. If the hallway is narrow, dinner is late, even if the stoves are blazing.
Perfect. And as models scale, those compare notes moments dominate total time. That's why the deck frames it as a multi-front war. Everyone is trying to build a faster nervous system for AI, because compute without coordination is just a very expensive argument.
Okay, 3 fronts. Walk me through them like I'm buying a house. What's the neighborhood? What's the inside the house? And what's the future weird extension someone outs later?
Neighborhood is the data center fabric, rack-to-rack, cluster-wide networking. Inside the house is the scale-up fabric, GPU to GPU links within a server. And the weird extension is the emerging frontier, new architectures and standards that change what a GPU system even looks like, including consumer clusters and optical packaging.
So we're not debating one cable. We're debating 3 different ecosystems with 3 different win conditions. That already explains why everybody online can be simultaneously right and insufferable.
Let's start with the cluster neighborhood. Historically, InfiniBand dominated AI training networks, massive market share, because it delivers predictable, ultra-low latency. The key metric called out here is small message latency, around 1 microsecond, which matters when you're doing lots of frequent, tiny syncs.
1 microsecond sounds like wizardry, but is that the whole story? Because I've seen teams pay for the fastest thing and then lose all the gains to bad tuning, bad topology, or, vibes.
And that's where the plot twists. The deck argues the landscape inverted. Ethernet is leading AI backend deployments, powered by RoCE and the Ultra Ethernet Consortium plus AI-optimized silicon. Tuned RoCE latency is framed around roughly 1.5 to 2.5 microseconds, slower than InfiniBand, but close enough for many training workloads when engineered properly.
So Ethernet is basically the minivan that got a turbo kit. Not as sexy as the supercar, but if it's fast enough and half the price, you start seeing a lot of minivans at the racetrack.
Exactly, and there's a credibility anchor here. Meta is cited as validating equivalent performance to InfiniBand on a very large Llama 3 cluster using RoCE. The claim isn't that Ethernet magically becomes InfiniBand, it's that the performance delta can shrink enough that other factors, cost, supply chain, operational simplicity, win the decision.
And now we get to the part executives understand. A chart with dollar signs. What's the headline from the 512 GPU cluster economics?
For a typical 512 GPU cluster, Ethernet is shown with over $1.18 million in upfront hardware savings and a 3-year total cost of ownership gap growing to $2.24 million. The deck even translates it into GPU math. That savings can fund something like 64 additional H100s or extend runway for smaller companies.
That's brutal. It's like choosing between a fancier highway and buying more cars. And in AI, more cars often wins because you can brute force the schedule, assuming the highway doesn't turn into a parking lot.
Now, inside the server, the scale-up fabric, NVIDIA's NVLink is framed as the gold standard. The key features: direct GPU to GPU communication without CPU intervention, a mesh-like fabric, and the eye-popping number, about 1.8 terabytes per second of bidirectional bandwidth per GPU in the latest generation cited here.
So Ethernet is winning the city streets. But inside the building, NVIDIA installed private elevators that move at superhero speed. And if you're training giant models, those elevators matter because you're constantly moving tensors between floors.
Right. And the standards world knows it. The deck highlights PCIe's response. Multi-stream architecture in PCIe 6.0, 7.0. The problem? Legacy controllers at very high signaling rates can create bubble cycles, basically wasted bandwidth due to serialization bottlenecks. Multi-stream processes multiple data streams in parallel to keep the link busy, improving utilization, called out as over 80% higher for complex AI traffic.
Bubble cycles sounds like my productivity after lunch. But technically, we're talking about the link sitting idle because it can't juggle enough independent work at once. So multi-stream is like opening more checkout lanes, not just making the conveyor belt faster.
And then there's the alliance move, UALink. The deck shows a stark gap. NVLink 5.0 at about 1800 gigabytes per second versus PCIe 7.0 times 16 at roughly 28% of that. UALink's pitch is use the PCIe 7.0 physical layer, but add a more efficient protocol stack optimized for accelerator-to-accelerator traffic, aiming for an open, high-performance scale-up standard.
So it's not just make PCIe faster, it's stop using a general-purpose protocol like it's a purpose-built race car. That's a very relatable engineering moment. The hardware is fine, the overhead is the villain.
Now, the emerging frontier, deconstructing the GPU itself. The deck argues the industry is pivoting away from massive monolithic dies toward clusters of smaller, light GPUs. Why? Yield and cost. Smaller chips tend to have higher yield. The slide claims up to 1.8 times yield improvement and nearly 50% lower cost per unit of compute with a modular approach.
This is the don't bake one giant cake, bake cupcakes philosophy. If one cupcake fails, you don't throw away the wedding. But cupcakes need a really good serving tray. Otherwise, you spend the whole party carrying frosting from one end to the other.
And that serving tray is optics, co-packaged optics, integrating optical engines onto the substrate to overcome shoreline bandwidth limits, basically the physical constraint of how many high-speed electrical signals you can route off a package. Optics helps you scale bandwidth without turning the board into a space heater and a noise generator.
And then the war shows up on the desktop, which feels unfair. We've got a Mac Studio cluster idea with unified memory and Thunderbolt 5, and then the classic enterprise personal supercomputer vibe on the other side. What's the real comparison here?
The slide frames two philosophies. One is local, efficient inference. Use RDMA and memory pooling over a consumer-friendly interconnect to act like a small cluster with a big shared memory story. The other is the NVIDIA approach, higher-end interconnect hardware, NVLink plus the CUDA ecosystem, optimized for raw training power and a tightly integrated dev environment.
So one path is make the stuff you already own cooperate, and the other is buy the spaceship, get the mission control software included. Both valid, depending on whether you're doing weekend experiments or trying to launch a model on a deadline.
And software is the multiplier. Two examples here. PowerInfer and EXO. PowerInfer exploits activation sparsity, keeping hot neurons in fast GPU memory while pushing cold neurons to CPU, so consumer hardware can run bigger models than you'd expect. EXO is about orchestration, peer-to-peer clustering of heterogeneous devices using autoparallelism and RDMA to make many machines behave like one inference engine.
This is the part people underestimate. They'll spend months shopping for GPUs, then ignore the fact that smarter scheduling and sparsity tricks can feel like you got free hardware. It's like reorganizing your kitchen, and suddenly you cook twice as fast.
The deck distills it into three trends for the next decade. First, the push for openness, alliances challenging proprietary ecosystems to prioritize interoperability and lower costs. Second, the physical barrier, copper hitting limits, making optical interconnects and CPO increasingly mandatory beyond the rack. Third, the primacy of software, sparsity and orchestration multiplying what existing hardware can do.
It's funny, the future sounds less like one giant magic GPU and more like a well-run organization, open collaboration, better communication channels, and smarter management. GPUs are basically becoming corporate.
And the strategic conclusion is refreshingly adult. There's no single winner. The fundamental trade-off persists: NVIDIA's vertically integrated proprietary stack versus a flexible, economical, increasingly capable open standards ecosystem. The right interconnect depends on the layer, cluster fabric versus inside the box, and on the workload's sensitivity to latency, bandwidth, and operational complexity.
So the advice is basically, don't pick a religion, pick a use case. If you're optimizing for absolute performance, you'll pay for it. If you're optimizing for scale and budget, you'll engineer around good enough. And either way, physics is waiting outside with a clipboard.
That clipboard is packaging and photonics. The next frontier is physical. Breakthroughs like CPO and optical links will decide who can scale bandwidth without melting power budgets. If you're planning infrastructure, the winning move is matching cost, performance, and openness to the specific layer you're building, and staying flexible as standards mature.
And for everyone listening, the next time someone says, just add GPUs, you can say, sure, what's your plan for the nervous system? Then calmly walk away while they Google RoCE.